So, in today's live session, we'll first revisit our discussion from the 10th live session that was concluded last week in a brief manner. Then, we will go through the discussion of week 11 content in a much simplified manner. And in between, I will provide you some questions relevant to the content. So again, similar to last week, since the lectures uploaded by NPTEL for week 11, we have already discussed in previous weeks, which were for retrofitting. To follow the initial module distribution that was presented in week 1, I will continue my discussion on seismic strengthening of infrastructure, where today we will discuss, we will have first an overview of seismic retrofitting, then we'll see seismic retrofitting of for existing infrastructure, wherein we'll see two classes of retrofitting: global retrofitting and local retrofitting. Then, for new structures which is yet to be affected by seismic attacks, we will see how different measures we can take to strengthen those structure. And finally, we will have some questions regarding the discussion that we'll do in the session. Okay, and finally, we will conclude the learnings drawn from the interactive session. So, in the last live session, we started discussing about earthquake induced damage and their retrofitting measure. In this, we first had an overview of two seismic events where we discussed how earthquake initiates, how seismic waves propagate, and how seismic waves damage infrastructure. We saw, like in the first image you can see, we saw from focus or from epicenter how the earthquake initiates, and how along the fault line, from hypocenter how the earthquake initiates, and what is the epicenter, the point just above the ground where there is a first contact of seismic wave, and the fault line where the energy propagates the maximum upon earthquake. Okay, we saw how wave propagate. For this, we saw seismogram, and we talked about Richard scale for how to define the intensity of earthquake. So we generally say that below, if the magnitude of earthquake as per Richard scale is below 5, it is not a very worry situation. However, above 5, there can be critical damage to the infrastructure. Then we talked about multiple examples on of earthquake damage, majorly for magnitude scale above 6.5. So we saw in various locations globally how say the different severe damage has been occurred due to earthquake, and how it has affected both the infrastructure and the livelihood there. Then we talked about how seismic assessment for existing infrastructure is important, and how it is carried out. So it involves a comprehensive examination of building structural system, material, construction method, and current seismic performance to identify potential weakness and deficiencies. So in this, we talked about visual inspection, historical review, structural analysis, geotechnical investigation, seismic hazard assessment, and risk assessment. Okay. Then, for existing infrastructure, how to identify vulnerabilities in the system which makes it prone to seismic induced damage. We discussed that also. So, based on the assessment, different vulnerabilities and deficiencies in the building can contribute to seismic risk. These deficiencies include weak structural system, poor construction quality, non-ductile construction material, soft or weak story, or irregularity in plane and elevation. So for all these, we saw how they are affecting infrastructure, and how they are making a structure prone to seismic damage. We then saw different ways in which distress can hit a infrastructure during earthquake event. So it can be in the form of a deep, wide longitudinal cracking, or differential settlement of foundation, or cracking along the fault line, or tilting of infrastructure owing to weak lateral strength. Okay. Understanding all these, we finally talked about how seismic strengthening of infrastructure, which is divided into three categories: either by improving the lateral road resistance, which can be done by adding new structural elements like shear walls and damping devices. Second can be enhancing the ductility, which can be done by strengthening the existing components and modifying connections. by foundation strengthening, retrofitting non-ductile member, and introducing moment frame, or by improving the energy dissipation capacity, which can be done by redistributing load, and this happens by if we use base isolation. Okay, so for all these, we had a brief overview kind of discussion. Additionally, we saw one case study also of a Salt Lake City building in western part of US, where base isolation was used for retrofitting the infrastructure, and we saw around 7 to 8 questions on the discussion that we had last week based on seismic damage and strengthening. Okay, so this was all that we discussed in the last session. The main crux of the session was understanding earthquake damage, its assessment, and its damage visualization. And we had a little overview of strengthening also. Now, elaborating over a minimal retrofitting discussion we did in the last session, different infrastructure requires different means for retrofitting. Okay, so when an earthquake strikes an infrastructure, the ideal choice of repair can vary from one infrastructure to another. So today we will discuss this aspect of retrofitting by understanding and organizing different special or different categories of infrastructure into different retrofitting methods. Okay, so to start with, it has been like observed that majority of these earthquake induced damage has may be safely reduced if they are converted into if the structures are converted into seismically resistant structure by employing few retrofitting measures. Okay. Now, the need of retrofitting of building arises under two circumstances. Either the building is already affected by earthquake, which is categorized as earthquake damaged building, or if the building is vulnerable to be damaged by earthquake, which comes under the category earthquake vulnerable buildings. So the second category have those buildings which are not yet experienced any severe earthquakes. Okay, so as an engineer or a consultant on site, we may need to strategize either of them. However, this being said, often structural engineer at site faces problem in taking decisions with respect to earthquake retrofitting. Why so? Because of following reasons: lack of standards or method of retrofitting. So generally, due to lack of standards or lack of knowledge regarding the retrofitting measures, there are often difficulties for choosing the correct method. Second can be doubts in effectiveness of retrofitting techniques, since there is a considerable dearth in the experience or the data of retrofitting structure. So this can also lead to doubt or ineffective application of retrofitting measures. And third can be absence of consensus on appropriate methods for wide range of parameters. Like if we don't have the knowledge or the experience to choose the appropriate method, like for which type of structure what measures should be taken, condition of material, how to take this into account, how to take type, amount, and location of damage into account before retrofitting, and how to consider conditions under which the damaged element can be retrofitted. Okay, so these are several problems that engineer often faces for choosing a proper retrofitting measure for a earthquake damaged building. So today we will see retrofitting measures against earthquake damage for both existing and already damaged infrastructure, and safe design measure for vulnerable, not yet damaged infrastructure. Okay, so first is seismic retrofitting of for existing infrastructure. So, in case of existing infrastructure, the need of retrofitting, or we can say the damage occurrence in infrastructure due to earthquake, may arise due to several reasons. Okay, these reasons are: earthquake has been designed according to seismic code, but the code has been upgraded, so your building is not more safe anymore. Okay, building was designed to meet the modern seismic code, but there is deficiencies that exist in the design that can make your structure vulnerable to earthquake damage. Inadequate consideration of strengthening measures, again, especially for essential buildings like hospital, historical monument, and architectural building, they can also offer risks for earthquake damage. Important buildings whose service is assumed to be essential just after an earthquake. So often, like once a structure is struck with earthquake, like people or engineers tend to neglect any damage occurrence and they continue using the service, which can make a structure vulnerable again for earthquake damage. Okay, building the use of which has changed over through the years. So if the functional performance of the building has changed, that can make a structure vulnerable to damage. Or building that has expanded, renovated, or rebuilt without considering seismic measures, those buildings are again vulnerable to damage. Okay, so, for such structures, various techniques of retrofitting has been developed and used in practice for seismic damage control. The basic concept of these techniques of retrofitting are aimed at upgrading the lateral strength of the structure, okay, or increasing the ductility of the structure, or increasing both strength and ductility. Okay, so as can be seen in the image also, when talking about performance of a structure, there are two aspects, okay, strength or ductility. So if we talk this in terms of seismic activity, my infra should either have high strength to bear the lateral load without much drift, or it should have a high ductility to absorb or transmit the seismic waves without collapse. Okay, so in both of them, both of them will follow a trade-off kind of relationship, okay, which will appear as a parabolic arc, as you can see. So either I need high strength or high ductility. Okay, so for an existing infrastructure with an undesirable performance, okay, its strength and ductility are below the minimum requirement of seismic capacity. Okay, so either we can increase the strength by maintaining the ductility, okay, or we can increase the ductility by maintaining the strength, or we can increase both. Okay, so if we do just strengthening, my shear strength of the building will increase with minimal drift, okay, as can be seen in this figure. Okay, so you can see here, if we just opt for strengthening, my shear strength of the building is increasing, and there is minimal drift in the building. Okay, and if we do ductility increase, so what will happen, though my shear strength will remain the same, okay, upon earthquake action, the structure's response to earthquake without enduring damage will improve. So my ductility performance of the structure is increasing, which will help me to survive the earthquake damage. Okay, and if we are doing both, like both shear strength will increase upon strengthening, and my ductility performance or damage endurance performance will improve in the infrastructure, which can be seen in this figure. Okay. Now, this decision to repair or strengthen a structure depends not only on the technical consideration but also on the cost or benefit analysis of the different possible alternatives. Okay. So, for a damaged infrastructure, there can be several alternatives that can be chosen. Okay. So, which alternative to choose, whether to repair, whether not to repair, whether to demolish, all the decisions depends upon not just the technical thing but also on the cost or benefit analysis of that structure. Okay, so generally it is suggested that the cost of retrofitting of a structure should remain below 20%, 25% of the replacement. Okay, as major justification for retrofitting. Okay, so if my cost of retrofitting is below 25% of the cost that would be incurred for the replacement, then it is suggested to go for retrofitting. Else, it is suggested to go for replacement. Okay. Now, for applying these previous on the in the previous slide, the measures that we discussed, either strengthening or ductility, for applying these measures on a structure, there are two ways. Okay, so there are two ways to enhance the seismic capacity of an existing structure. The first is a structure level approach of retrofitting, or we can say global retrofitting. Okay, this involves global modification of the structural system. Okay, so globally means throughout the structure. Okay, and second is a member level approach of retrofitting, or we can say local retrofitting, and this deals with increasing the ductility of components with adequate capacities to satisfy their specific limit state. So this member level approach or local approach is something which is related to a particular segment of a structure and not global, and not is not applied globally to the structure. Okay, so in these two major categories, a structure can be retrofitted, okay, to bear the seismic activity. We can see these things in the flowchart also. Like in these two categories, there can be different possible techniques that we can opt out. So, like we can see in the global retrofitting techniques, there is addition of shear wall. Okay, there can be addition of infill walls, adding bracing, adding a wing wall or buttresses, wall technique, mass reduction, and supplemental damping and base isolation. So all these techniques that was just highlighted to you in the last session, they all come under global retrofitting measures. Okay, and in local retrofitting measures, what all comes? Jacketing of beams, jacketing of columns, jacketing of beam column joints, and strengthening individual footings. So these all things come under local retrofit. Okay, so today what we'll do, we'll discuss all these measures in a little more depth. Okay, for global and local retrofitting, and we'll see how these measures are comes like plays an important role in different categories of infrastructure. Like if I talk about adding shear wall, what all different types of infrastructure are generally uses this measure to retrofit a building, or to retrofit their structure against seismic activity. Okay, so let's first discuss the global retrofitting part. Okay. So generally, a global or a structural level retrofitting is applied when the entire structural lateral load resisting system is deemed to be deficient. So if the entire structure is deemed to have deficiency in lateral load carrying capacity, then we opt for global retrofitting. Okay, and the common approach in this regard is to increase the stiffness and the strength of the building with limited ductility. So when we are talking about global retrofitting, we are more focused on strengthening the structure rather than improving the ductility of the structure. Okay, now global retrofitting can be done in different ways. Okay, so let's just quickly see each of these ways one by one. Okay, so first technique can be adding shear walls or infill walls or buttresses. Okay, so aim of these things is to increase the lateral strength of the infrastructure. Okay, and while opting for these techniques, we must keep in mind the we must keep in mind to determine the existing capacity of the structure, or the increment requirement, or and estimation of post increment behavior considering increase in dead load. Okay, so these three technical points shall be taken into consideration while choosing for these three measures. Okay, like existing capacity of my building will help me to decide how much lateral strengthening I require. Okay, and once we apply these measures, there will be increase in the dead load of the system also, which can again hamper my infrastructure in other ways. So that thing also needs to be considered before opting for these techniques. Okay, and for construction, at the time of construction, it is important to locate where the elements needs to be added, how to design the wall, and how to connect it with the existing infrastructure. So these three things becomes important when we execute these techniques. Okay, now often adding shear walls or infill walls or buttresses are used for buildings, bridges, and industrial facilities for seismic strengthening. Okay. Now, where in the past was such addition of shear walls and all have been used for seismic strengthening? So, there are two of many examples of some special infrastructure that we will see today. Okay, so these are the two examples where shear walls or buttresses was used for seismic strengthening. Okay, so the first case is a iconic skyscraper structure. Okay, in America, where shear walls were added to strengthen the building's lateral load resistance capacity and reduce the sway during the seismic event. And these shear walls were strategically placed in the building's core and along its perimeter to enhance the structural capacity. Okay, and the second example you can see. Transportation bridge in San Francisco, where again, uh, as a part of retrofitting project, buttresses were added to the bridge existing piers to enhance its lateral stability and resistance to seismic force. And these buttresses help the structure to dissipate seismic energy and reduce the risk of prior displacement or failure of during the earthquake. Okay, so these are like two major examples of some special infrastructure where uh, either adding shear wall or use of buttresses was like uh, taken into consideration, were considered for seismic strengthening of the structures. Okay. Now another way to globally retrofit a infrastructure can be adding steel bracings. This method can be used for both concrete structure as well as steel structure. Okay, and its aim is to increase the moment resistance capacity of the infrastructure. Okay, now what things that needs to be considered while choosing these steel bracings, the factors include much lighter in weight, so these bracings are much lighter in weight, so the problems like increase in dead load capacity of the structure won't be coming here. They can be effectively used in a location where large opening is required. So this is a one more technical advantage that steel bracings offer, which needs to be considered while choosing this technique. And while constructing these technique, the connection to existing infrastructure needs to be taken care of, and available dead load capacity of the infrastructure should be known so that we can decide how many braces can be provided or is needed. Okay, and such bracings are often used in skyscrapers and high-rise buildings. Okay, so they find main application in high-rise buildings. Okay, now, third measure of global retrofitting can be wall thickening or mass reduction. So again, its aim is to increase the strength or ductility of the building. Okay, and the main advantage of using wall technique of mass reduction comes in the form of minimal disturbance to the existing infrastructure. Okay, and while using these techniques, one must keep in mind locating the places for operation. Okay, such that it can cause minimum it can it can have minimum effect on the functional capacity of the infrastructure. Okay, so these things need to be taken care of while choosing this technique, and it mainly finds its application in masonry structure and residential building. Okay, so for masonry structure and residential building, if we want to strengthen the infrastructure against seismic activities, generally wall thickening and mass reduction technique is used. Again, if we look at some special existing infrastructure where these measures are opted, so first we have the Salesforce Tower in San Francisco, where which underwent seismic retrofitting by including steel bracings to improve the seismic performance. Okay, then there is this historic structure in Rome, Italy, a masonry structure, okay, where wall thickening was used as a measure to improve the seismic resilience while preserving the architectural integrity. And the third case is a California Medical Hill Center, where again wall thickening measures was used to improve the seismic performance of the structure. Okay, so in this ways, these are some like special or iconic structures where the previously discussed techniques have been used for seismic strengthening. Okay, another way is the use of base isolation. So as we have already talked about base isolation in the last session. Okay, it is a powerful and a relatively cheaper method of seismic rehabilitation of in buildings. And how it is done, it involves the use of rubber bearings. Okay, so a rubber bearing consists of a laminated layer of rubber and steel plate strongly bonded together during vulcanization process of rubber. Okay, so rubber is the main thing that absorbs the vibrations coming from the ground. Okay, and they are designed with a vertical stiffness usually 300 to 1000 times higher than the horizontal stiffness. So they have a very high vertical stiffness, however very low horizontal stiffness, which helps them to vibrate upon earthquake. Okay, and such a system increases the first natural period of both in horizontal direction in the range of 1 to 2.5 seconds, and the response acceleration decreases accordingly. So due to the high vibration capacity in the horizontal direction as a result of low stiffness, the natural period of vibration in the horizontal direction increases, which lowers the load that will be coming on the infrastructure, which lowers the vibration load that will be coming on the above structure, and in this way the response acceleration decreases in the infrastructure. So the application of this we saw in the last session also when we talked about the city county building. Okay, and the bearings can be provided either in mid-story elevation or above foundation. So these base isolation they can be done either above foundation or at some mid-story level. Okay, so for mid-story level, how base isolation is applied? So first step is to remove any finishing from the surface of the column. Okay, so suppose this is a column. So first step is to remove the finishing from the column. Then we provide steel encasing across the column cross section. Why this is done? Because since we will chip off some column area to accommodate our base isolator, we need a replacing strength bearing source also in the column for a temporary period. So this is just like a scaffolding kind of thing for the column. Okay, once we have encased the column with steel plate, what we'll do, we'll chip off the column original cross section from the mid story level. Okay, so here you can see some column concrete area was chipped out from the mid story level. Then what we'll do, we will install our isolator pads. Okay, and we will connect them with the existing column through grouting mortar, and then finally we'll remove the steel encasing that was done from on the side. Okay, so in this way a base isolation is done at the mid story level. Okay. Now, for base isolation, just done above the foundations, like say pile foundation, how we do that? So we will first excavate the soil from the sides. Okay. Then we will increase the footing area. Why? Because since installation of base isolation will take away some of the foundation area, so just to have enough foundation strength for the above structure, we need to increase the area of footing. Okay, then what we'll do, we'll cut off the central control pile. Okay, then we'll set a escalator. Okay, which is a kind of a metal plate kind of thing assembly. Okay, over the pile surface. Okay, then we'll set the base isolation pad. Okay, and then we'll connect it with the top column again with one more scalar. Okay, finally, we'll cut off the remaining piles also and isolate the footing from the above structure. So this isolation now what it does, if there is some vibration in the ground that is happening, those vibration will be transferred to the rubber pad. My rubber pad will vibrate with a higher time period, and due to this my structure will receive less vibration energy, and it will vibrate with a very low time period, which will safeguard the structure against heavy damage that could have occurred due to high vibrations. Okay, so this is how base isolation is carried out in a structure. Now, another method for global retrofitting is the use of supplementary damping devices. Okay. So most used approaches to add supplementary dampers to a structure is installation of viscous dampers or viscoelastic dampers or frictional damper or hysteric dampers as a component of a brace frame. So you can see in this image also, like in between two floors, such uh, temporary or supplementary damping device are often installed. So what they do, they vibrate at a much higher time period, and they reduce the vibration energy that will be transmitted in the main structural members, and it will safeguard them for having any failures. Okay. So, a common application areas of these base isolation and supplementary damping devices comes under buildings, bridges, and transportation infrastructure. Okay, the example of this method, supplementary damping device and base isolation, was used in the Salt Lake city and county building in the Salt Lake City also, that we discussed in the last session. If you remember, in the last session we had a very brief, detailed discussion of this building, how for different floors also some seismic measures were taken. So those some seismic measures was nothing but supplementary damping devices, and how near the foundation, by scrapping of the joining between the footing, how a base isolation, like around 400 base isolations were installed in this building. Okay, so like these were all global retrofitting measures, starting from adding shear walls or infill walls or buttresses, then coming to steel bracings, then talking about wall thickness and mass reduction, and finally talking about base isolation and supplementary damping devices. So these all techniques, they come under global retrofitting, and by global retrofitting we means a measure that is applied to increase the lateral load carrying capacity of the complete structure when my whole structure is deemed of the strength. Okay, now we will talk about local retrofitting measures, or the measures that are applied to a certain a section of infrastructure only. So, the approach here is to upgrade the strength of a member which is seismically deficient. Okay, in global, we saw that my whole structure is seismically deficient, so we need to opt for a global measure. Here, if my some components of the structure is seismically deficient, then we go for local retrofitting, and this approach is more cost effective compared to structural level retrofitting. Why? Because it is applied only to a smaller area of the infrastructure, so it costs less. Okay. Now, to accomplish local retrofitting, we have jacketing or confinement. Okay. Now, this is something that we have discussed quite a few times throughout the course. Okay. So whether it is a like kind of steel plate jacketing or FRP jacketing, we have already discussed what is jacketing. Okay. So the main purpose of jacketing, if I highlight again, is to increase the concrete confinement, especially for circular cross section columns. So due to confinement, what happens? The cracks that are coming, that are growing inside the columns, they are arrested and they won't propagate further. So it helps the structure to bear the collapse. Okay, to increase the shear strength of the column, also due to jacketing, the shear strength capacity of the column is increased, like we saw in the FRP jacketing of columns. Also, when we discussed FRP jacketing, we saw how it is used as a measure to increase the striation and to increase the flexural strength provided when they are well anchored at the critical section. Okay, so they can also increase the flexural strength or capacity of the building, like in case of long columns which is under the threat of buckling. Okay, so due to confinement, what happens? It provides an additional strength bearing component to my column, which will increase the flexural strength of the column. Okay, so if we talk about different components of a building, where jacketing is used for as a local retrofitting measure for seismic strengthening, for column, we can do jacketing in different ways. Okay, it can be done as a concrete jacketing also. It can be done as a concrete jacketing where concrete encasing is done on the existing column. Due to this concrete jacketing, what happens? My cross sectional area of the column increases, which increases its load bearing capacity. Okay, and this increases the strength of the column. Okay, then there can be steel jacketing. Okay, where steel plates are used to confine and strengthen the column, and similarly there can be strap jacketing, where instead of plate we use steel strips with the filling mortar in between to strengthen the column. So these techniques we have already discussed in the part in the past when we talked about retrofitting measures. So these can also come as a measure for seismic strengthening. Apart from this, for beams and slab, if they are taken as a single unit, we can have three-sided retrofitting or four-sided retrofitting, three-sided jacketing or four-sided jacketing. Okay, so again, the aim here is to increase the cross-sectional area of steel, okay, or the reinforced concrete, and which will increase the strength or and the ductility of my member, which will strengthen its, which will increase its load bearing capacity. Okay, for joints, which are the most critical element, when we talk about lateral stresses, we can opt for longitudinal steel jacketing along with double ties near the joints. Okay, so either we can use just longitudinal steel jacketing for increasing the strength of the joint, or we, along with the longitudinal steel, we can use double ties at the top and the bottom also to increase the joints lateral load bearing capacity. And for columns, we can also have FRP encasing to increase the strength. Okay, so this is something we have already discussed in the past. Okay. Now, some cases where these methods, these local retrofitting methods were used in infrastructure, some very special infrastructures. The few examples include the Ashaki Kakio Bridge, one of the longest suspension bridge in the world. Okay, so in this, the bridge tower and foundation are reinforced with steel jackets and concrete encasements to enhance the resistance to seismic forces and to prevent structural damage during earthquake. So these local retrofitting measures were opted in this structure to increase its seismic performance. Then there is a historic uh, structure in Istanbul where confinement techniques, by like including reinforced concrete jackets and steel reinforcement, were used for stabilizing the building's wall and the dome. So here also local retrofitting measures were used. And if we talk of some major infrastructure in India where retrofitting measures are used, these local retrofitting. So, case 3 shows Mumbai Pune Express flyover in Maharashtra. So, in these flyovers, for certain columns which were deficient of seismic strength, local retrofitting measures like FRP confinement was used to strengthen the structure. While for CSMT, Chhatrapati Shivaji Maharaj Terminus in Mumbai, also some local retrofitting measures was used to increase its shear strength capacity. Okay. Now, so this was all about how using different means we can strengthen a existing infrastructure, okay, which has already undergone damage or which is very vulnerable to get damaged in the near future. Okay, now suppose we know about the historic condition of a place, okay, and we are constructing a new infrastructure at that place. Okay, so during design or construction only, we can take seismic strengthening measures, which will help me to make a which will help me to prevent my structure for undergoing before undergoing any damage. Rather than protection, if we take measures during the design, we will have a preventive technique. So now suppose we like in such cases, we that comes under earthquake vulnerable structure category. There are different points to be taken care of while designing the infrastructure, and if these points are taken care pretty well, then the risk of earthquake damage in the structure will be reduced. Okay, so what are these points? The first point includes the reinforced structure. So, in incorporating reinforcement bar within the concrete structure enhances its strength and ductility, that we already know. Okay, so for designing different elements of a building like beams, columns, and strength to withstand seismic forces, it is like it is prescribed to use reinforced concrete, okay, so that it can have both strength and ductility. And these prescriptions are often you can find in the design code also, like in IS 1893, which is the code for seismic design of a building. In that also, it is prescribed to use reinforced concrete rather than plain concrete for construction. And second point is flexible foundation. So design foundations to allow for movement during an earthquake reduces the risk of transfer of seismic forces to the superstructure. So if my foundation is flexible, it will be able to take more earthquake vibration. It will dissipate less vibrations to the superstructure. So utilizing techniques like base isolation or use of flexible materials in foundation can help us to enhance the seismic resilience of the structure. Okay, seismic isolation. So, introducing seismic isolation system to decouple the structure from ground motion will reduce the risk of earthquake, as we have already talked in base isolation. So, IS 1893 also provides a guideline for selecting and implementing seismic isolation devices such as elastomeric bearings or sliding systems. So, such systems are also prescribed by the Indian codes, which should be used for isolating the structure from the foundation in places where the seismic activity is a very big threat. Okay. Another way can be use of damping systems by incorporating damping devices within the structure to dissipate energy and reducing structural vibration. This we have already discussed. Proper anchorages. So guidelines have been provided in IS 1893 and IS 13827, which recommends design and installation of anchorage system to enhance the structural stability. So anchoraging, we already know what anchoraging is, and those anchoraging, if they are done properly, can also help us to make our structure vulnerable, safe from seismic activities. Then another point is redundancy in structural elements. So incorporating redundancy in structure system by providing alternative load path or backup mechanism can ensure the safety of the structure during earthquake. And different elements with sufficient redundancy to withstand local damage has been outlined in the IS codes also, which one can go through. Rigid joints. So if the design structural connection and joints to maintain stiffness and resist deformation. Okay, so generally joints are made stiff to resist deformation during seismic loading, and proper detailing of connection, mainly the beam column or the slab column joints, is very essential to ensure structural stability. Okay. Another way can be the use of lightweight materials. So, utilizing lightweight construction material like autoclaved aerated concrete or light steel framing can also reduce the mass of the structure, which can help us to mitigate the seismic forces. So, if anyone has any idea about IS 1893, the vibrations that occur in a building, they are directly related to the load of the building also. So if we can decrease the load of the building, then also we can decrease the vibrations that will be occurring in the building. Okay. And compliance with the building code. So if we adhere to the national building codes and standards like IS 1893, IS 4260, and IS 13827, to ensure seismic design and construction practices, uh, we can have a structure earthquake resistance. Okay. And compliance with the building code ensures that the structure are designed, constructed, and maintained in accordance with the established principle and regulations to enhance the overall resilience of the building and for public safety. So even if all these points are properly carried out, these all things come under one major category, that is compliance with the building code. So all these building codes, they should be properly followed during the design phase, so that my building can be made safe from any earthquake damage. Okay, so in this way, we have discussed both categories of a infrastructure. The structures, those are damaged due to earthquake. How for those structure, different measures can be chosen for different kinds of building. So we understood that. And for structure which is yet to be damaged by building or which are yet to be constructed, what all different measures that we need to keep in mind for choosing a safe construction practice. Okay, so this was all about seismic strengthening as a for retrofitting and repair of a seismically damaged infrastructure. Okay, and this was all for today's session. Any doubts in the discussion today that we had? Any doubts to anyone? So the major aim of the session was to focus on how we can categorize different kinds of infrastructure into different categories of seismic retrofitting. How we can see a structure as a global retrofitting project, and how we can see a structure as a local retrofitting project, and globally how we can categorize different techniques for retrofitting, and locally how we can choose different techniques for retrofitting. Okay. If anyone has any doubt, they can like post their queries now in the chat box. Okay, so we will discuss them post the end of the class session. Okay. In the meantime, if you have queries, you can write in the chat box. For those who don't have any queries, let's see some question to understand whatever we have discussed today, so that you can have a clarity of whatever we have discussed today. So these are for first few questions. Just try to read those questions and try to get what should be the answer, and then we'll discuss. Okay, so I will wait for one minute for you guys to think. Read the question, and if you know the answer, write the answers in the chat box, and we'll see the solution. Okay, I will freeze my screen and I will mute myself for 1 minute. Okay, so let's see the solution to these questions now. So for the first question says, ask us what are the primary objective of seismic strengthening for newly developed infrastructure. So in the just in the discussion we saw like different measures that needs to be taken for a newly developed infrastructure to make it safe from seismic strengthening. However, the main the main objective, the primary objective is to ensure compliance with current seismic design code and standards. Okay, so if this is done, if this is taken care properly, then a structure will be safe from any earthquake damage. Okay, so this is important for newly developed infrastructure. Okay, so answer will be A. Now, second question asks us which of the following technique is commonly employed for seismic strengthening of infrastructure, existing infrastructure. So, first is base isolation, increasing structural redundancy, lightweight construction material, and seismic monitoring system. So, for existing infrastructure, the answer can be base isolation. We can opt for base isolation also, or we can use any seismic monitoring system which will help us to decide uh, how much damage has incurred and what kind of retrofitting measures we can take. So the correct answer will be base isolation only, but one can also think of monitoring systems which is also employed for getting the knowledge whether strengthening is required or not. Okay. Third question is, what is the main purpose of seismic retrofitting or existing infrastructure? So the main purpose is to bring older structure to the current safety standard level. So for any existing infrastructure, the purpose of retrofitting is to make the structure safe for seismic activity. And how we can make the structure safe against seismic activity? If we can get the structure to the stage where the current standard stands. Okay, so the current standards, like provisions, what they say, if we can get the structure up to that level, we can make the structure safe from seismic event. Okay, so these are the three answers. So let's see few more questions like this. Again, I will mute myself for a minute and then we'll see the answers. Okay, so let's see the answers for these questions also. So, which factor is crucial for determining the level of strengthening required for special structure? Proximity to fault line, annual precipitation level, available of natural resource, and population density. So, the main factor, main crucial factor is proximity to fault line. Okay, so the structure which are more near to the fault line, they are more vulnerable to get again get earthquake damage. Okay, so this can be very crucial factor for determining what level of seismic strengthening we require. Okay, which seismic strengthening technique is typically more challenging to implement in existing infrastructure compared to newly developed infrastructure? Seismic isolation, damping system, reinforcement to structural elements, or flexible foundation? So the answer will be seismic isolation. So generally for existing infrastructure, it is very difficult to like it will be more time consuming and difficult to install base isolation systems as compared to newly developed structures. So like in newly developed structure, we can, while constructing the foundation only, we can include the base isolations. However, for existing infrastructure, we need to cut off the foundation, then install the isolations, which can be more challenging sometimes in application. Okay. The sixth question is, what is the primary advantage of incorporating seismic strengthening measure into the design phase of a newly developed structure? So the answer will be to improve the to enhance the long-term performance and resilience against seismic events. Okay, so this will be the correct answer. The primary advantage of incorporating seismic strengthening measures while design is to enhance the long-term performance. So if the structure or the locality near the structure have histories of earth seismic damage, then including these seismic measure initially they may seem to be a waste of money, but however in long term they can provide many critical advantages to the structure, which during the seismic events. Okay. Now, just we have two more questions. So, again, I will mute myself for a minute and then we'll see the answers to them. Okay, so let's see the answer for these two questions also. Which of the following special infrastructure sector often require customized strengthening solution? Hospital and healthcare, residential building, commercial office, and recreational park. So among these categories, hospital and healthcare facilities are often require seismic strengthening solution. Why? Because they are more critical or more associated with the life of a mankind. Okay, so like they are a more critical structure basically. So they need some special requirements initially during the design only, so that there is no loss of life due to seismic event later on. Okay, which aspect is typically assessed during a seismic vulnerability evaluation of existing infrastructure? So while evaluating an existing infrastructure, the important thing that is assessed in the infrastructure is the structured material strength. What is the strength of my material, whether it is adequate enough to take lateral load or not? So this is the main point that is assessed when we are talking about assessing the vulnerability of the existing infrastructure. Okay, so these were some questions related to seismic strengthening. So these questions are like more very general questions, and they will help you to get that thinking of seismic retrofitting. Okay, I haven't went very deep into seismic retrofitting, seismic design and all, because this is a like separate code, separate course kind of thing. All seismic, like how seismic damage occur, how much seismic damage is occurring, how much seismic force is acting on a building, this all comes under is 1893. Like how to design, how to get how much load is occurring at different floors and everything. So if one is familiar with is 1893 and all, they will understand this session more properly. Okay, so just concluding this session, we discussed about two categories: earthquake damaged building and earthquake vulnerable building. In earthquake damaged infrastructure, we talked about global and local strengthening. For global strengthening, we saw different methods that can be provided and different special infrastructure across the globe where these methods were used. In local strengthening, we talked about confinement, and we saw different infrastructures where confinement was used as a seismic strengthening. And finally, we highlighted several measures that can be taken care of while designing an infrastructure only, which is vulnerable to seismic activity in the future. Okay, so this was all for week 11. Thank you.